Or did you just like put
I
the
switched the
1
16 to 30.
instead?
No, I switched the 30 to 16 in one part. I put like, not days, like in this part. I put 60 days, 30 or 3.
Okay.
This
Okay,
one's
so let's get started on lesson 31.
Do we get to keep these?
Yes, you do.
They are.
I would argue that
Excuse me?
one section of this section may be the most, I don't know, it's probably the most important thing we'll see between now and the rest of the final, or for this semester. In the next month, it may be the most important thing in this section. It deals with symmetry. Reflections and translations. This is all geometry stuff, yes, but we're going to be relating it to the XY plane. Yeah, no, this is good stuff. You'll see, this is good stuff. Now, do you have an idea of what symmetry is? Whoops. Right? Do you have an idea of what symmetry is? Like that triangle appears to be symmetric about that line. Of course, it would not be symmetric about that line. You can think of symmetry as, can you fold it and it would fold right on top of itself. Here it would not. Reflections, you can think, ooh, I have like a mirror here, and I can take an object and reflect it about my mirror. Right? Do you remember doing this in geometry class where you like reflect an object? Some people like this, the tracing paper. Yeah? Anybody like that? Okay, 1, 2, and a finger. We had 2 hands and a finger.
A finger or a finger?
Yeah, right?
Sorry.
A finger. It was a finger. Yeah, a finger, not the finger. Translations. These are whenever you're moving something. So you're taking an object and then you're going to move it some number of units up, some number of units down. That's what a translation is. We're going to deal with all of these things on the XY plane. Now, if I look at this guy here, finished. That's bad.
It's like, who's there?
I know, I was like,
little offensive.
Yeah.
If I look at this parabola, I'm going to say, and I think this is really pretty simple to say, this is symmetric about the y-axis. Because if you look at the y-axis and you fold this parabola, it's going to fold right on top of itself. Now, why is it symmetric about the y-axis? Because this is symmetric about the y-axis. Now, why? We can answer this. Here's a point on the guy here. He's the point A, comma B, over A, up B, right? The fact that he's symmetric means that if there is a point over A, up B, there is also another point that is left A, up B. Isn't that what symmetry is all about? For every point that's over a certain amount and up, there's another point on the other side over that same amount and up. That way whenever you fold, they touch. Any point on it. So when you're symmetric about the y-axis, A, comma B, and negative A, comma B are on your graph. Basically, for any y value, you could have an x value that would be positive and an x value that would be negative. That's what it means to be symmetric about the y-axis. You could just as easily have something that was symmetric about the x-axis. I could draw, whoa, that's not. Better? Better. It's not perfect, but it's better. This is just a relation, it's not a function, but that's okay, we'll still talk about it. This relation actually has the equation x equals y squared. If you remember, a parabola has the equation y equals x squared. This is just the reverse scenario. If it was opposite day, this is not related to the content directly, but if it was opposite day and you switch the x and y axis, like, right, you'd have this. So if you just switched x and y, you'd have that. Right, these are just the reverse x. Okay, anywho, when you look at this guy, he's got a point that's over a up some amount. And now what's the point got to be down here? You tell me what he's got to be. This point's going to be a comma negative b, yep. So when you're symmetric about the y-axis, a comma b is on your graph, so is negative a comma b. If you're symmetric about the x-axis, if there's a point a comma b, then there's also a point a comma negative b. These are both on the graph. And herein lies a test for symmetry. Herein lies a test for symmetry. If you replace x with negative x, and the function reads the same, you replace x with negative x, and the function reads the same, what does that mean? This means that you are symmetric about the y-axis. Look at the criteria for being symmetric about the y-axis. To be symmetric about the y-axis, if you had a comma b, you'd also have to have negative a comma b. Well, that means if you replace x with negative x, you should get the same function in return. Example. Y equals x squared. Rather than taking x times itself, take negative x times itself. What do you get when you take negative x times negative x? Positive x squared. Right? I put in negative x and I got the same thing back, right? I replaced x with negative x and the function reads the same. Therefore, in geometry, did I ever show you the therefore symbol? Did I ever do this? Did I ever show you that? Ooh, fancy, fancy. In math, when you put I don't know why this developed, I have no idea. Don't ask me that question. But these three dots in the shape of like an equilateral triangle means therefore. That's like mathematical jargon. What's that?
Invisible triangle.
Yeah, it's an invisible triangle. You can imagine a triangle there. So, therefore, y equals x squared is symmetric about the y-axis. Because when I replace x with negative x, I get the same thing back in return. That means for every point at a comma b, there's another point at negative a comma b. What about this? You could have a test for y-axis symmetry. If you replace y with negative y, and the function reads the same, what does that mean? Replace y with negative y, well that's this guy over here. B and negative b. Well, if the function reads the same here, now we're symmetric about the x-axis. Example. X equals y squared. Replace y with negative y. That's actually the example I drew up on the board first. Replace y with negative y. What do you get? Instead of y times y, you'll get negative y times negative y, which is exactly the same as y times y. So, when I replace y with negative y, I get the same thing back in return. Therefore, x equals y squared is symmetric about the x-axis. It's a simple test. Can you think of a function that wouldn't be symmetric about any axis? What about y equals x plus 1? That's a line with a y-intercept of 1 and a slope of 1. Do you agree that's not symmetric about the x-axis or the y-axis? If it's symmetric about the y-axis, when you fold it, it should fold on itself. If you fold this, it doesn't fold on itself. If you fold it this way, it doesn't fold on itself either. It's not symmetric at all. This is not symmetric about the x, and this is also not symmetric about the y. You can see it. I'm going to prove it to you algebraically. Watch me prove it to you. It'll be fancy.
For those, how can you be sure that even if like those 2 points are symmetric, what happens if like one side, like on AB, what if the next point up goes over, but the other one stays on the parabola and they don't line up?
Right, so you could, now, because what you're saying here is, what if I go C, and this is C comma D, but down here it's C comma negative D plus 1 or something? Yeah. Well, the way I drew the picture, I drew a parabola that was symmetric. What we're doing here, when we replace x with negative x, do you know what x is? No. She just said, I'm going to replace any number with the opposite of that number, and it still comes out right. That means that this works all the time, no matter what the x is. I could plug x equals 0, x equals 1, x equals 2, x equals 4, x equals 5, x equals 10, and it's always going to work. So what we proved, whenever we sub x with negative x, we're not just testing a particular case, we're actually testing every number at the same time, which, the power of math, right? I was just going nuts with the Algebra 1 students today, whenever we graph like x is greater than 2 or something, and I was like, every that you move when you do your graph, you just ran over infinitely many numbers. And I was like, isn't that neat, right? Because if you actually tried to list all the numbers that make this statement true, you would be taking a long, long time to do it, right? But the neat thing is in math, we can just say, whoop, there it is, right? Infinitely many things, boom, done, right? Same thing here. What we said is, we replaced x with negative x, and do we know what x is? No, it could be anything. Do we know what negative x is? Well, we know it's the opposite of that anything. And what we found is, if you take the opposite of that anything, you get the same thing as if you did that anything. Well, that means for every x, there's a negative x. Symmetry everywhere. Pretty cool, my opinion. We just tested every number. Whoa, right? Mind blown, right? Now, we can do the same thing here. If we want to test that it's not symmetric about the x-axis, replace y with negative y. I always remember this one, it's not the way you wished it was. You wished you'd replace x with negative x. I remember this is not the way I wished it was. When you bring the geometry into the algebra, sometimes it doesn't work the way you wished it would. But now, if I replace y with negative y in this function, I get that. If I rewrite it, it looks totally different. Totally different. And think, if I flip this thing around the x-axis, it would actually be that line, if you really think about it. If you flipped around the x-axis, you'd have this line, which is y equals negative x minus 1. And that is not the same thing. If it's not the same when you reflect it, it's not symmetric. And you can see that it's not symmetric because those are not the same equations. This line and that line are different, not symmetric. How do you test if you're not symmetric about the y? Replace x with negative x, and you'll get y equals negative x plus 1. That's not right either, because that's not the same as what we started with, not symmetric. This one, if you flip around the y-axis, you'll end up here. This is y equals negative x plus 1. And you would agree, if you flipped around the y-axis, that's what you would get. And that's not what you started with, so it's not symmetric. Kosher? Now, what if you just wanted to reflect something? You could do that too. Because what I just showed you is, while this guy and that guy are not symmetric, they are reflections. Because reflections and symmetry are completely related. If I do reflect this, I end up with that. It's not the same, so it's not symmetric, but this and that are a reflection. Let me be clear about it. So, y equals x plus 1 and y equals negative x plus 1 are a reflection, and in particular are a reflection about the y-axis. Why? Because I replaced x with negative x. Now, they're not the same, so since they're not the same, this implies that the function is not symmetric, but it is a reflection. I can reflect any function. If the reflection comes back the same, it's a symmetric function. But if the reflection comes back different, well, I just reflected it. So technically, I could take any function and reflect it, and I could have y equals x squared plus 2x plus 1. If I want to reflect this about the y-axis, I'll just go y equals negative x squared plus 2 times negative x plus 1, and get y equals x squared minus 2x plus 1. These guys are reflections. And what are they reflections about? They're reflections about the y-axis. So if you took the one and you took the other, actually, if you graph these two, I'll just show this for the sake of, because these are actually easy to graph. Well, these are easy for me to graph at this point in my life, so I will graph them for you just to show you. One of them is a parabola here. This is y equals x squared plus 2x plus 1. And this one is a parabola there, y equals, x squared minus 2x plus 1. If you reflect it about the y-axis, that's what you get. It's kind of neat, right? And that's what we just did. And we did it without even looking at it. We don't have to see it. The power of algebra. You don't have to see it, and it can actually happen. Power of algebra. Power of geometry, you can see it. Right? Until you get up to higher dimensions, and then you can't see it anymore, but you can imagine it. Because most math anymore is done on n-dimensional spaces, which could be any dimension. And we can only see 3 dimensions, but you could imagine higher dimensional spaces. You'd have to have a really good imagination, but you can do it. Anywho, I just didn't want to make the claim that you can see all geometry. But geometry at a basic level is you can do it and see it. Algebra is you can do it and not have to see it. We'll get to translations next time. That'll be Friday, tomorrow. For tonight, take a look at 31. Section 31, take a look at, oh, by the way, I did say this in class, very simple property, listen to me though as I say this. If you are symmetric about the x-axis, and you are symmetric about the y-axis, you're symmetric about the origin. It's a fancy word for things that are symmetric about the x-axis and the y-axis. What are we? Archibald?
The unit circles.
Oh, nice, okay. Maybe this isn't a unit circle, but that's Archibald's big brother. That's Archibald with type 2 diabetes. Okay. That's a bad joke. Okay. Anyways, here we go. Let's do 6, 7. That's insensitive. 11. 12 and 14. It's going on the internet. Oh my gosh. And also take a look at 19 and